Go ahead when you're ready.
All right. Well, thank you very much, Tracy and the Holden team, to have me on and for the invitation. Thank everybody for coming in and spending some time with us. We have kind of a neat uh, lunch and learn today that's going to kind of broadly tackle the kind of controls and applications. The fun part about this one is we would need a month of Sundays to really dig in and go into the minutia of controls and the different applications available to them. But what I wanted to do was pull together some common information that we all need to get these projects working together. So really, that's the kind of the point of view I'm taking today. So I'll kind of just run right into it. My name is Greg Allen. I'm an application engineer here at Greenheck, and happy to be spending some time with you. All right. So agenda. First thing we're going to do, and kind of what I consider the most important, is how do controls communicate? If you have a widget and another thing, how do the two talk to each other so that systems work? All right. So I want to break out some common lingo, some common methods, and really knock out so we're all on the same page of what is common. And I say common because there's other ways to do things, right? Some of them are way less common today. Some are just outside of my wheelhouse. So we're going to start off with that information. Then we're going to move into using some standalone controls and some applications that we can draw pictures to and all be on the same page with. We're going to end with some question and answers. So if you have some questions, throw them in that chat box, and we'll wrap those up at the end. All right, start off. We have two gentlemen on the screen, and they're talking, right? And our left gentleman is speaking French, and the right gentleman is speaking Greek. Um, if those are the only languages they know, the one thing they're not doing is communicating. They're just talking at each other. And really, I wanted to start here because there are different languages that different controls speak. And one of the things that I come across, I assist our customer service teams when there's a trouble call. And sometimes what I'm running across is device A won't work with fan B. And it's like, well, are we saying the right things? Are we communicating the right way? And this is really easy to miss. But if you have some of the key lingo, we can start tightening up designs, sequence of operations, specs, drawings, fan schedules, if you have some of the verbiage to throw on it. So now, if we're going to relate this to the HVAC industry, let's say I have a controller, right? A controller is anything that's going to make decisions and take control. And then I have the controlled. That the controlled could be a fan. It could be a makeup air unit. Could be a motor starter. And for us to communicate between the two, we have to be using the same language. Now, many devices have more than one way to talk. But now it is on the engineers to look at what I'm sending and how I can send it, and what I'm receiving and how I receive it. Right. So that is the key to making devices work together. And once you have a controller and a controlled working together, you can do amazing applications. So I'm going to kind of work right into this. Right off the bat, the most common way of talking in our industry from device to device is kind of a binary method, right? It's a true false statement. It's a one or a zero, a yes or a no, a start or a stop, right? Those are our only two options. Now, there are two common ways of sending this binary command communique. And the first one is a dry signal. All right. So, anytime you are reading through a submittal on a certain piece of equipment and you see that dry verbiage, what they're saying is on the sender's end, it's saying that I'm closing a relay, I'm closing a set of contacts, making continuity between those 2 points. On the receiver's end, you're saying I can recognize when there's a broken circuit or a complete circuit. That's the 2 sides of that. Now, our other one here is a voltage signal. And this is very common as well. Like I said, these are the 2 most common. A voltage signal is, hey, I'm going to send power when I want you to do something. I'm going to take it away when I want you to stop, right? True, false, start, stop. Now, those are the 2 most common, but where we can immediately run into a problem is, let's say I have a carbon monoxide detector, and it's going to close a terminal when it's an alarm, right? So it's saying, hey, I'm an alarm or I'm not an alarm. Now, whatever's receiving that, if it's sending power, that may work. If it does not have a dry signal receiver, then it may not understand it. So this is really where you kind of need to line things up. And I'll go a step deeper here. When you say a voltage signal, some things, let's say the receiver, it only understands 1 voltage, some devices, right? If it only understands 1 voltage, that's your control voltage. And let's say it's 115 volts. This means that every other device that is communicating with it, that it's receiving, has to send 115 volt. Anything less, anything more could be detrimental or just not communicate. There are other devices on that voltage side where they typically aren't using the power at all for anything. They don't power themselves with it. It's powered by something else. It's just recognizing there is or isn't power. And typically that's a 2-wire system where 1 wire, your common, is 0, and your second wire is carrying a voltage. And it's just saying, hey, they're either both 0, which is stop, or one's 24, 12, 115. It's different than the common. So that's a non-power robbing type system. And I just kind of want to point these things out because this is where I usually see most of the downfalls or miscommunications is, product A is sending 12 volts, product B needs 115. Now we have a problem. We have to have a translator to get the 2 to communicate to each other. And those translators typically, they can be seen up front. And I congratulate anybody that catches this up front. It makes your install go so much smoother. But if you didn't catch that, this is one of those things that's going to take a couple of days, get some parts in, maybe a transformer, and you're making a translator at that point to convert one signal to another. The other thing I want to say about the dry side is, let's say I'm that carbon monoxide detector again, and I'm just closing a contact. Well, if my receiver is speaking dry, that's great. We're done. 2 wires. It's a complete circuit. It's a broken circuit. But let's say that carbon monoxide detector actually sends 12 volts. Now we have to verify that the contact on the carbon monoxide detector can handle 12 volts going through that dry contact. So you have a kind of a step deeper. You may have to look into things. If one's sending power, can the other one take that power? Can it take that amperage and that voltage? And typically right in the IOMs of those products, it will define the terminals and the capacities of those terminals. All right. So that is just our first way of communicating. Now we're jumping into a modulating system. In a modulating system, I could be communicating so many things, right? The 2 most common are 0 to 10 volts, typically DC, or 4 to 20 milliamp, right? With this type of communication, I could be presenting to you, hey, what speed to go, what position to go to, what parts per million you may have. This is in our industry, we use these all the time, right? Because it can provide a range of data. But again, we're back to making sure we're speaking the same languages, or we're going to need a translator, right? So if I have a an EC motor that accepts a 0 to 10 volt signal, and that's both a go command and a speed reference, right? 0 to 10. I need something sending a 0 to 10 signal, hopefully intelligently, that tells it what speed to go. If my system that is a sender is, well, sending 12 volts, it's binary. What is the motor going to do with, well, I see 12 volts, I guess I'll go full speed. It might be a voltage that actually harms it because it's expecting 0 to 10. So it's important, again, to know what command type am I using. And now the last one I wanted to throw in here is it kind of that full boat data communication protocols, right? And I threw two up on the screen. They're the two most common that I see, and that's Modbus and BACnet. Now, this is not just start stop or go 50%. This is actually a full-blown communication conversation that can be had between sender and receiver, right? What temperature are you at right now? And I can report back temperature. How's your day going? It has the ability to actually go through, and as long as there's a parameter that it can ask about, the device can respond back using these protocols. Now, like I said, there are other protocols, and this webinar is not intended to be a catch-all for everything. A few common ones, I guess, besides what I have on the screen, like LonWorks would be another one. I don't rarely see that anymore. But here on the screen is really when I look at the equipment that like me as a manufacturer provide, or I look at equipment that I need to interact with, this really kind of captures 99% of everything. So let's kind of take this information and everything we do from here out. I want your mind to come back to this screen. What signal are we using? Are we using the same one? So let's look at the controllers or the senders, right? A controller, typically uses logic, to start and stop and maybe even define speed, right? But a controller could be anything from, well, a light switch to a building automation system, right? If it's a light switch, you personally become the logic behind it. You want it to run or don't run. If it's a building automation system, I mean, wow, the world is your oyster at this moment. A building automation system or building management system, kind of derivation, can take sensory input, environmental input, what temperature, humidity, time, pressure, relative pressure. It can take all those different characteristics or criteria into itself. It can use logic that's been pre-programmed to say, if this and this and this, then do that. And that becomes the output. The output is typically, either a voltage, I'm sending 24 volts on this terminal to go to this device to tell it to run, or I'm sending a 0 to 10 volt signal on this terminal to this device to tell it to run and how fast to go. Also, a building automation system, it kind of typically has that one more step where it starts communicating with the user. It provides data that you can access from around the world, right? So we have a lot of capabilities and some really cool things we can accomplish with a building automation system. But there's a lot of time where we're doing a project where the capabilities needed are shy of all that awesomeness, or even the budget is shy of all that awesomeness. But we're looking for a piece. I'm looking for a function that's a little higher end, a little bit smarter. And that's where we get into different types of controls that are available and standalone controls. I'm going to come back to that in a couple slides. All right, so if we have controller, sender, we also have the receiver, right? Or the controlled. Here's 4 common things. Like I said, this is not a catch-all. These are common ones I deal with. But the most simplistic of a receiver is typically a relay, right? A relay is going to accept a voltage, a coil voltage. Well, here, I'll throw the diagram up on the screen. It'll accept that coil voltage and that from, well, the controller. And when it's activated, it's going to take and change state for the normally open, normally closed terminals, right? So really, if we look at this diagram, I am accepting a wet or a voltage signal, and my output is continuity between, well, B and C or A and C, depending if I'm activated or not. So now I can change paths. If A and C, this happens over here. If B to C is connected, this happens over here. You can get relays in so many different ways. Most of the electricians that I know have, a box of these in their vans, and they're creating kind of a mechanical logic using them. They can do amazing things with them. But in the end, you have single pole, double throw, single throw, double pole, double throw. There's a lot of different types of relays. You can have multiple terminals, so you can control multiple things. But really, in our industry, becomes kind of the core, the most simplistic controlled device. There are some other devices out there, like let's say motor starters, right? I'm a fan manufacturer for the most part, and I have to turn a motor on and off, right? If it's an AC induction motor, a motor starter that's amazing. I have controllability. I can send it a voltage, or I can create a dry contact closure. If I have the right starter that can read those types of signals, it will activate its own contactor, which is kind of a big relay, and pass power to the motor. So now it's got motor control built into it, and I'm able to remotely take control of that. Well, and then also motor starters have protection. That's a big part of their job is to look at the amp draw and make sure that that motor is running healthy and to turn it off before you have a really bad day. But in the end here, okay, all the way back to that first big slide, controller and controlled. Am I sending the right signal to this motor starter for it to engage the motor or not? Right. And there are some starters that you need a specific voltage, control voltage to tell it to run. There are other motor starters out there that have both a voltage input as well as a dry input. So if you have, if your controlled has 2 ways of communicating, you're twice the chances of actually having success. All right, so really, we're going to step into drives. This is just an example of a VFD. VFDs, we're starting to get to where it's got its own brain, and they're programmable. You have programmable inputs and outputs, right? So we're getting more capacity. Now, most drives, and I'm going to say most because I don't know every drive out there, right? But a lot of the drives I deal with, you can tell it to accept a dry contact closure for an enable or start, right? Or you can tell it to a different terminal to accept a voltage input. That's a start stop. Also, a lot of drives have an analog input where I can say, hey, I'm sending you a 0 to 10. So if there's a voltage, that's a run command. And if it's a voltage between 0 and 10, that's also a speed reference. I want you to run and at 50% because I sent 5 volts. Typically that 0 to 10, by the way, for a speed reference, it's typically linear. So I send 5 volts, that's asking for 50%. If I send 10 volts, it's asking for 100%. 0 volts typically is saying stop. Also, a lot of some drives, you can flip what kind of modulating input it's expecting. And you can say, hey, I want to send you a 4 to 20 milliamp signal. All right, so now it's going to accept that as both a run and a speed reference. And I'm going to throw up here on the screen, what I call Vari-Green motors, specifically EC motor technologies. Most all of these have the ability to accept a 0 to 10 volt signal. A few on the fringes can accept a 4 to 20 milliamp signal, but the vast majority is 0 to 10. And I wanted to throw these up there as kind of their own line item because they're not so much programmable, especially the small ones. They just have a 0 to 10 input. And that's because every EC motor that's out there actually has a drive built in it. Otherwise, it'd just be a permanent magnet motor if you had an external drive, I suppose. Could look at it that way. So EC motors have drives. That drive gives it, the ability to accept either a potentiometer or a 0 to 10 volt signal for speed reference, soft start, as well as all your motor protections, right? Because it's a drive, it has motor protections is built into it. So these are common controlled items within our industry. I'm throwing this up here on the screen because, again, going back to that original dry, wet, modulating backnet, if you go to the manufacturer's provided information, quite often you can find information about those products that says, hey, you want a 0 to 10, or I'm talking backnet, right? So this information is going to line up and say, hey, this device sends or receives these types of signals. And you may find, it's a common product, but there's variants of it. And that variant, which is usually defined by the model name, it gets longer and longer. That is actually saying, okay, this is the 0 to 10 version. This is the wet input version. I just highly recommend going back, looking up the installation, operation, and maintenance manuals or the submittal sheets that come with those different products to make sure that as a designer of systems, you are seeing both controller and controlled and making sure they can speak. All right, one more little subset, and this is just devices, right? So we got controller, controlled. We also have devices, and devices typically provide information to the controllers, right? And this could be, a temperature sensor, a time clock, a motion detector, volatile organic compound sensor. Devices are just those ancillary things that pick up information about the environment. Maybe it's a relay would fall into the devices as well. Also, I'll kind of add one more thing here. I didn't hit it before, but many pieces of equipment have an auxiliary contact built into them. So when that piece of equipment is running, it closes its own terminal, aux contact. And those aux contacts can be read by something with a dry input. Many times those aux contacts, they're going to define, up to 250 volt at 10 amps. They're going to give you a rating that you can pass power through it. So kind of that aux contact also falls into this realm. All right. So that was all the fun with kind of building a foundation of typical communication types. And when you communicate, sender and receiver, control and controlled, right? So let's break this down. I have a wealth of experience in our Vari-Green control set, which are a good example of standalone controls as well. So just kind of reiterate, if you have a building automation system or that's part of the plan, awesome. Almost every one of these control or applications that I'm going to walk through, you could do with your BAS and a couple of devices, sensory input. You can do the same thing. But if you have scenarios where the building management is not a part of the project scope, here's where some of your standalones can pick up that higher end function or a piece of it and run standalone. All right. So, like I just said, building automation, take input from other devices, programmed with logic, control the output depending on what inputs are telling it, um, communicate and display information. And that communicate and display is, like I said, across the world to whoever is necessary to see what fans are running, what lights are turned on, who's accessed the building. All that information kind of can be wrapped up into one massive controller. So here we go into standalone controls. All right. Right off the bat, I'm going to start off with a real simple application, right? So I've got a welder's bay. We have a person, welder helmet. They're doing their job. They have a need for exhaust. Well, sometimes the most simplistic controls are actually exactly what you need. That welder doesn't likely need 10 different criteria to define the speed of the fan. You can put a remote dial in the space and let them pick. I want to move more or less air. I'm welding galvanized today. I need to move a lot more air. I need to control my arc more, so I'm going to reduce the airflow and improve the weld. That puts them in the seat of the decider on how much air needs to move. And of course, with like a remote dial, you can go in and you can define what realms you can work between, your minimum and your maximum. So maybe you're creating that overall guidance for the welder. They can choose anything between these 2 points. But in the end, they're just playing with a switch or a potentiometer, right? So really wanted to start out simple. We don't always need to overdo it. Here's a good sequence of operations. Just kind of a quick write-up for you as an engineer is trying to communicate what your intent is and what has to work with what. In this scenario, I'm just calling out there's a 3-wire I need between these 2 products, and the potentiometer is going to set the speed. All right, so let's go a little bit trickier, right? Now we're exhausting a locker room, right? We have a beautiful rooftop exhaust system there. And I got my wiring, and there it is. I've got, for this scenario, this locker room exhaust, I am moving different amount of air depending on, and my criteria and the controller I picked is a VOC, or volatile organic compound controller. Now, a VOC controller, there's between 5 and 10,000 known VOCs, right? And a lot of those odd, let's say, smells, those incorporate VOCs. And this is why you typically will find, volatile organic compound sensors in like locker rooms, bathrooms. Carbon monoxide is a VOC, so I see them in garages every once in a while. Now, the neat thing here is that VOC controller, it is not just a sensor, but it's a PID brain with its own sensor. So it's going to look at the environment, like this one, it can sense about 5,000 square feet for area. It can see what the level or the quality of the air is in that space. And it takes your input, your set point of what level of air quality do you want to maintain. And the worse it gets in that environment, the higher the fan's going to run. So I see that a lot in like I said, locker rooms, etc. And you can see kind of a quick sequence of operations. In the end, it's a control. It needs to be powered. These are powered by 24 volts. Great. And it kicks out a 0 to 10 volt signal. So that's my output. So I'm being powered by 24. My output is a 0 to 10. I'm sending it to a fan. This would be, say, a Vari-Green fan. EC motor accepts the 0 to 10 volt signal. Great. We're sending and receiving the same communication. All right, let's step this up a little bit. Oh, I'll just reiterate. This is one way to do things, folks. I'm not telling you the only way or the way that meets codes in your area. Just wanted to kind of bring that up again. This is one method of doing controls. All right, so let's say I have stairwell pressurization, i.e. there's a fire, I have a stairwell that I need to pressurize, typically to 0.1 inch. I'm going to push air into that. I'm then going to have, a relief or an exhaust fan. And I need to control by either controlling the amount of air I'm pushing into the space or by controlling the amount of air I'm allowing out of the space. I'm going to maintain that positive 0.01 or 0.1 inch of pressure so that the stairwell maintains pressure, smoke stays out of the stairwell, and I have a safe egress for the people in the building. So this sounds like a kind of a complicated, scenario, but really it's not so much. So on the left, I have my exhaust fan. In this scenario, I'm going to say that my supply is constant, and my exhaust is varied. Like I said, it could be, I'm controlling the exhaust or I'm controlling the supply, either way. But in this, I have a motor in a fan that is being controlled by exhaust, and it's hooked up to a constant pressure controller. Now, a constant pressure controller, kind of the same as that VOC in a way. I have a brain of a PID controller. Only difference now is its sensor that it's looking at is differential pressure, right? It's saying, what is the pressure in the stairwell compared to in the space, right? And maintain that differential. So it accepts your input, maintain 0.1, and it outputs a modulating signal. And the neat thing about the modulating signal here is if doors are open or closed, your pressure changes in that stairwell. Well, using a differential pressure transducer or a constant pressure controller, I can recognize that and modulate the speed of my supply or exhaust air to maintain that environment. Now, also on this one, I did have a fire alarm relay just kind of drawn in. And that's because even though this is a stairwell, 100% of its life, there's not always a fire. So in some applications, you may want to run a fan at a lower point just to maintain airflow. You may want that system standalone and it's separated. So only when a fire alarm goes off does it actually start controlling the pressure in that space. Like I said, there's 100 ways to get each of these done. I'm just kind of showing you standalone controls and a way to look at it and think. But again, I'm just using a 0 to 10 volt signal as my communication method. Let's look at a dryer, a commercial dryer, and really this could be bathrooms in an apartment as well. If you look at the way this is thrown up, again, I've got the exact same fan, I've got the same wiring, I have the same control. This is a constant pressure controller. But on the right hand side, you can see my dryers. You can see bathrooms that are they're pushing air into a common riser. So here, what I'm going to do is I'm going to always look at 2 points of pressure, right? I'm going to look at my pressure in the ductwork, the common riser, and I'm going to compare it to, ambient air, ambient in the space. Now, I can make a simple statement like, maintain negative 0.06 inches inside the ductwork compared to, the open rooms. Now, that kind of statement says, if a dryer turns on and it starts pushing air into the duct, great. The pressure is going to go up as that air volume comes in. The controller is going to recognize that and it's going to speed up that fan. And because it's a PID loop, it's going to speed that fan up until I'm actually maintaining my set point, negative 0.06. And then I'm not going to go any faster. I'm just going to wait there. And if a second dryer or a second bath fan turns on, pushes more air in there, it's going to recognize the need to speed that fan up even more. So this is a way for you to have, say an exhaust fan on the roof, and I'm going to, instead of moving 100% of the air all the time when maybe only one person's doing laundry that day, I'm actually running and only moving the air I have to move, not all of it. And now I don't have to make up all that air that I'm exhausting as well. So this is, I look at this and say, I could do this just as well with a building automation system. I could take a BAS, I could take a differential pressure transducer. Those two can talk. I can have someone program that BAS to maintain a set point, and I can use another output from the BAS to go to an EC motor or to a VFD and send a 0 to 10 to it. I can do all these applications on that higher end. But in this scenario, I just had no need for all that ability and expense. I'm going to do it with a little standalone control. All right. I'm going to introduce one of our controls quick before I go into the next application, just so we're all on the same page. What you see on the screen here is just our Greenheck Vari-Green hand-off auto control. And the reason I want to show it to you is because it has multiple inputs. You can see dry input, voltage input. It can just accept that simple signal, that binary signal from other devices. No matter what it is, if it sends voltage or creates a continuity, I can read that. And then this control allows you with the up and down arrows to set your speed. So I can set my speed and I'm turned on and off by something remotely. This is truly akin to kind of a higher end motor starter that this type of fan wouldn't need. And then my output from an HOA, again, is a 0 to 10 volt signal, which, well, everything Vari-Green responds to a 0 to 10, or other VFDs or all kinds of things do. All right. So with that said, my next application is a municipal garage, right? I've got this big garage, big doors, trucks can come in, get worked on, trucks go out. And kind of my theory or my sequence for this is I want from 8 to 5, maybe 9 to 5. This is municipal. From 9 to 5, I want a certain amount of airflow just for the people in the bay, right? So that means I'm going to incorporate a time clock, a simple time clock. From 8 to 5, turn on. I can set my speed right on the device. It takes the go command and the speed reference that you use the arrows to get to and creates that 0 to 10 to control that fan, that VFD. All right, let's make it just a little harder. Let's say, well, this is a spot that they're going to have trucks pulling into. Trucks emit carbon monoxide. All right, so let's have a second speed that responds to an alarm condition. And this has actually got a terminal. We call ours the override terminal or fireman's override terminal. In the end, it's a second speed that takes precedence over any other function if it's activated, right? And in this scenario, that's a good call. Whether it's 8 to 5 or not, if there's a high carbon monoxide content, I want to be able to respond to that. And I'm going to go to a full speed, a purge speed per se. But this has got two official set points for speed reference that you can plug right into it using the 3 buttons on the face. All right, just a little more complicated. Let's bring in the topic of interlocking, right? Because when we interlock things, we're basically saying that these two things have to happen at the same time, or this can't happen if this hasn't happened as well. So in this scenario, if I'm going to move that air, I have an actuated damper, right? And this is going to allow outside air to replace the air I'm exhausting. In this scenario, the purple lines, I'm showing that I'm grabbing power from somewhere else, whether it's 115 volt or 24 volt, back to those, specs and the lines on the fan schedules, actually defining what the required voltage is really helps things line up and the lack of transformers needed in the field. So in this scenario, let's say I have a 115 volt actuator, which uses power in the bay, so no transformer needed. I'm using the aux contact or auxiliary contact of this device, the HOA, that changes state, that it changes state whether it's running or it's stopped. There's 2 points. If it's running, I'm passing that 115 volt to the actuator. It opens the damper and the exhaust fan runs. So I'm interlocked. I'm controlled by a timer. I have an alarm state or a second speed, and my output is a 0 to 10. Now, the last thing I'll point out here is that time clock. Most of the time clocks I've dealt with are just a set of contacts, right? It closes or opens. There's no power sent. So that's a dry. So I'm going to put that into the dry input. Carbon monoxide alarm systems, I've seen them both ways, both dry and voltage inputs. So, all right. That's a good application to kind of show off how all these different things can work together without a super brain computer being part of the building. This is just your damper exhaust interlock. Kind of wanted to point that out. But in this scenario, I also have a makeup air. So I don't want my exhaust to run unless my supply air is pushing in, right? So in this scenario, I'm saying that the makeup air has a 24 volt output when it's running. And I'm going to read that 24 volts on my voltage input of this control. And that's going to activate both my damper and the fan. So kind of, again, hitting that interlock idea. All right. How about a warehouse? Well, sometimes you don't need fancy there either. Sometimes you do. Depends what your sequence of operations is. Here, picture a warehouse. Someone walks in the door. They're going to be getting some stuff out of the building. You could have a mechanical switch, a light switch that just flips on. But in this scenario, again, we're talking about keeping away from miscommunications. The fan on the roof is a Vari-Green fan. Awesome. I need something to send it a 0 to 10 volt signal, right? I need to tell it when to go and how fast to go. In this scenario, my translator that I kind of brought up earlier, if you're speaking 2 different languages, light switch, open, close. If it's powered, power, no power, right? It's sending Greek and my fan is looking for French. The HOA in this scenario becomes the translator between those 2 devices. I'm accepting my binary and I'm outputting a modulating. All right, I threw a lot at you folks, and I threw a lot at you without trying to get too deep because I want to apply this knowledge to as much as possible. In the end, I encourage you to have well-written sequence of operations. And if you can, you look in at the submittals and make sure you're lining up, your sender and your receiver. They can both speak the same language. Many times a device will have, 2 different ways of sending, and a receiver would have 2 different ways of receiving. Hopefully one of those 2 line up. If they don't, this is your first key to work with your contractors or work with the manufacturers to find what piece is missing so that when we get to install day, we can have a smooth process, minimize the number of phone calls, and just make everybody's day. So what I'm going to do here, I'm actually going to, well, here's my last screen. By the way, anything I brought up today when it comes to controls for Greenheck, there's some really neat videos on greenheck.com and YouTube. I encourage you to go check them out. You get just a little bit more in depth than what we had time for today. But I do want to open the floor for questions.